All right, everybody. I have 5 practice problems for you here that deal with these mutually exclusive ideas and overlapping ideas and using the addition rule. Okay, so I'm going to work these 5 problems out for you. Follow along with me as we go here. All right, so this first problem says, Misty rolls a 6-sided die. What's the probability of Misty rolling a 1 or an even number? Okay, so if I wanted to write this in probability notation, right, I would say, what's the probability that she rolls a 1? Remember, or is this U right here, okay, or an even number. Okay, so that's how I would write that. These 2 events are mutually exclusive, meaning they don't overlap. Okay, so what that means is I can just find the probability of each one of those and add them together. Okay, so the probability of her rolling a 1 is 1 out of 6. Okay, and the probability of her rolling an even number is 3 out of 6. There's 3 even numbers on a die, right? So since these are not overlapping, all I have to do is add them together, right? So 1/6 plus 3/6 is 4/6. Which can be reduced to 2/3, because you have a common denominator there. Not a common denominator, a common factor between 4 and 6, which is 2. All right. Okay, so let's look at the second one here. So this says, Ricardo spins a spinner that has 5 equal sections numbered 1 through 5. So it probably looks something like this. Obviously, this is not very well drawn by Miss E, but that's essentially what it looks like. Okay, with the numbers 1, 2, 3, 4, and 5 in them. Okay, so we want to find the probability of him landing on a 4 or a number greater than 2. Okay, so if I wanted to write this in probability notation, I would write it like this. Probability of rolling a 4 or rolling a number, I'm going to use an abbreviation, say greater than 2. Okay, so that means rolling a 4 would be selecting just this one right here, okay? But then rolling a number greater than 2, I have multiple options, right? I have 3, 4, and 5. So notice that 4 gets selected twice here, okay? So the probability of rolling a 4, which I'm going to change this to orange because it's a little hard to see, is 1 out of 5, okay? But the probability of rolling a 2 is, I have 3 out of 5 chances here, right? But I can't have this 4 counted twice, okay? So what I have to do, remember, the addition rule says I would add these 2 together, and then I have to subtract out the overlap, right? What they have in common. So they have in common 1 out of 5, right? So this right here is the probability of rolling a 4 and having it be a number greater than 2, right? I'm subtracting out the intersection, okay? So you have 1 plus 3, which is 4, minus 1, which is 3 again. So 3 out of 5 would be your probability for that one, okay? All right, so let's take a look at number 3. Okay, these are going to get a little bit more complicated as we go. Okay, so 3 says, you randomly choose a card from a standard deck of 52 playing cards. What's the probability of choosing a spade or a diamond? Okay, so we have to think about, are those 2 events overlapping or are they mutually exclusive? Okay, it's not possible for a card to be both a spade and a diamond at the same time because they're different suits in a card deck, right? So those 2 events are mutually exclusive. Okay, so again, what that means is all you have to do is add the probabilities of the individual events together. Okay, so the way I would write this is I would say this is the probability of pulling a spade or pulling a diamond. Okay, so for each suit, there's 13 cards in each suit, right? Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Queen, King. So 13 out of 52, and it'll be 13 out of 52 for each of these. Okay, so all I'm going to do is add these together. 13 plus 13 is 26. So I have 26 over 52, okay, which does reduce to 1/2 if you wanted to reduce that, okay? All right. Okay, let's take a look at number 4. This one gets a little bit tricky here. Okay, so we have Miss Campbell asked 137 men and 203 women about the color of their bedroom. Of the ones surveyed, 57 men and 130 women said that they have a beige bedroom. Okay, so the question is, if a person is randomly chosen from those surveyed, what's the probability of choosing a man or a person who does not have a beige bedroom? Okay, so let's go ahead and write the probability notation here. So we want to find what's the probability of choosing a man or, so union, someone who does not have a beige bedroom. So remember, we can indicate that with a little superscript C, which remember means complement. It literally translates to the word not, right? That's what it means, okay? Like that's what the symbol means. You could also notate it, remember, you could also write it this way with a little dash right here, right? It means like not or the opposite. Okay, so the next question I have to ask myself is, are these two events overlapping or are they mutually exclusive? Okay, so these two events are overlapping, right? It is possible in this survey here for her to randomly select a guy, a man who does not have a beige bedroom, right? Okay, so what I'm going to have to do here, okay, is figure out a couple of things, right? Because they didn't tell me in the problem exactly how many people don't have a beige bedroom. They only told me how many people do have a beige bedroom, okay? So I'm going to do a little bit of like side math over here, okay? And I'm going to use this space here. So I know there's 137 men and 203 women. So this here and here. So I know that my total number of people is, I'm going to add those together. 137 plus 203, right? And that's 340. So I have 340 people total, okay? Now I need to figure out how many of those people have a beige bedroom versus how many do not have a beige bedroom. Okay, so for my beige bedroom, they did tell me that, right? They had said 57 men and 137 women have a beige bedroom. So I'm going to add those two together to get the total number of people who have a beige bedroom, right? So if I add those up, I get 187. Okay, now my only two options in this survey are, do you have a beige bedroom or do you not have a beige bedroom, right? So the way I can figure out how many people don't have a beige bedroom is to subtract the total and the number of people who do have a beige bedroom, right? Because those are my only two options, right? So I have 340 minus 187, and that gives me 153. Okay, now the reason I did all of that, if you recall, okay, is because when we are doing problems like this with the addition rule and you have overlap, right, you have to subtract out what these two have in common, what these two categories have in common, so that we don't end up counting people twice, okay? So let's do each individual part, right? So the probability of each of these individual events. So the probability of her selecting a man is 137 out of 340, right? Because there's 137 men total, okay? The probability that we pick someone who is not in a beige bedroom is here, 153 over 340. Okay, so those I can add together, but I have to subtract out however many people here we have in common. So the men who also don't have a beige bedroom, okay? So that's the one other thing we have to go back and calculate. So I have 137 men. Right, I'm going to do this up here. So I have 137 men. Okay. And then 57 are men with a beige bedroom. So if I want to find the men without a beige bedroom, right, men and those men who do not have a beige bedroom, I'm going to subtract these two, right? Because again, no matter what gender you are in this scenario, you either have a beige bedroom or you don't. Those are the only two options, right? So the total number of people in each of those categories has to add up to the total in the group, right? So if I subtract these, I get 80. So that is the number of people that these two groups, man and not beige, have in common. Okay, so you would add 137 and 153, and then which is 290 if you add those two together, and then you have to subtract 80 from that. So 290 minus 80 is 210. Okay, so 210 out of 340. And we could reduce this a little bit if we wanted to, just by getting rid of those zeros, but we can leave it as it is. All right. Okay, last one. I'm going to help you set this one up, and then I'm going to have you all kind of try this one out on your own here, okay? And this one's a little bit tricky because you have to list all of the possible outcomes in order to make this make sense, okay? So we have Mary here, and she's going to roll a 6-sided die twice, okay? So I want to know what's the probability that the sum of the two rolls is a prime number, or at least one of the rolls is 5. So she gets so that one of those rolls is a 5. Okay, so okay, all right. So the best way to start this out first is I want to list all of my prime numbers, right? So if she's going to roll a 6-sided die twice, the largest possible sum is 12, right? 6 plus 6. So I need all of the prime numbers from 1 to 6, or 1 to 12, sorry. So my prime numbers here from 1 to 12 are obviously 1, 2, 3. 4 is not a prime number. 5 is a prime number. 6 is not. 7 is a prime number. 8 is not. 9 is not. 10 is not. And then 11 is a prime number. Okay. And then 12 obviously is not. Okay. So here's how I'm going to do this, right? What I want you to do here is take a second to list out all of the possible combinations of these two dice rolls, right? So like I would have 1 and 1 would be my first one. And then I could also roll a 1 or a 2, 1 and a 2, a 1 and a 3, a 1 and a 4, etc. Okay, so I'm going to pause my video. Go ahead and pause yours. List out all of those possible combinations of numbers, and then circle or label somehow the ones where the sum is one of those prime numbers that I have listed. Okay, so try this out, list all of those, and then check back with me to see how you did. All right, y'all. So what you see listed there, kind of in the bottom, like right part of my screen, is all of the possible combinations of rolling 2 dice, right? So there's 36 possible combinations here. The things that you see circled in purple are all of the prime numbers. So like when you add the two numbers in the same circle, they give you a prime number. So like 1 and 1 is 2, which is a prime number. 2 and 3 is 5, which is a prime number. 6 and 1 is 7, which is a prime number. Okay, so there's 15 of those total. So the probability that I select a prime number sum here, is 15 out of 36. Okay. Then what you see underlined in red is the probability of the sum, right? Or like having those rolls having at least 1 5 in it. So that could be 1 5 or both of them could be 5s. It's just, it has to have at least 1 5. So that's what you see underlined in red. So here I have 1 5, 2 5, 3 5, 4 5, 5 5, 6 5 in this row right here. And then obviously you have 5 1 5 2 5 3 5 4. This 5 5, obviously I'm not going to count it twice. And then you have 5 6 down here. Okay, so there's 11 of those total. Right? And obviously we can see that some of these overlap, right? For example, right here. Okay, we have a couple of those that overlap. So we can go through and actually pick out all of these that overlap. So there's one, here's a second one, here's a third one right here, and then here's a fourth one right there. Okay, so the probability of both, so prime and having at least 1 5, so I'm just calling that a 5, is 4 out of 36. Okay, so obviously these two events are overlapping, right? So if I want to find my final probability here, is the probability that I select a prime sum, or at least 1 5. The way I'm going to do that is add the two individual categories together. So 15 over 36 plus 11 over 36. And then I have to subtract out the ones that were counted twice, because I don't want to count them twice. So minus 4 over 36. Okay, so 15 plus 11 is 26, and 26 minus 4 is 22. So my final probability here is 22 divided by 36, which you can reduce if you want. They have a common factor. Both of those numbers can be divided by 2. So 22 divided by 2 is 11, and then 36 divided by 2 is 18. Okay, so that would be like my final answer there if everything is reduced. All right, y'all, so I hope this was helpful for you in looking at different scenarios where we can use our overlapping and mutually exclusive ideas along with our addition rule. So I'll see you in the next one. Bye, everybody.